All right, welcome back, folks. I hope you all did well on your last test. As we begin the final unit in the class, I want you guys to know that we're going to start talking about some things that are really used a lot in statistics and in things that you'll read. And I think that you'll find this section is relatively simple in terms of construction, and it's going to lead us into what we'll do over the next few weeks and for the rest of the class. Hypothesis testing involves a few fundamental steps and a few fundamental pieces, and we're going to talk about that in this section. And I'm going to kind of break it down piece by piece. And then in the next few sections, we're going to work through some different types of examples, and we'll talk about how to use hypothesis testing from now until the end of the class, essentially. So in this section, we're going to talk about the difference between the null and the alternative hypothesis, I should say alternative. We're going to talk about how to state conclusions and how to determine the significance of hypothesis tests. And then we're going to talk a little bit about type 1 and type 2 errors. Now, as you will see in any research that you read, it's really important that you have a well-defined research question in order to understand the data you collect and in order to communicate the results of your findings. This course has nothing to do with writing research questions, but you're about to learn how to use those research questions or how to use a hypothesis test to answer those research questions. Okay, so the question is your roadmap for the hypothesis test. Everything you need to know about what you need to do to set up the hypothesis test is in the research question. Okay? It is the question that your hypothesis test is going to answer, okay? And it's the way you're going to frame your conclusions. At the end, when you're finished, you should be able to answer that research question. You should be able to have an answer for whatever it is that you're trying to find out. When we talked about probability many weeks ago, we briefly discussed the idea of rare, unusual events. We use this idea in statistics and when we do hypothesis tests because we use it to determine if things are unlikely to happen. So as researchers, we generally set what's called a significance level, okay, and it's given by this letter alpha. As researchers, the significance level is the line that we draw where we say that something is unlikely to happen by chance alone. We generally set that to be 5% in behavioral research, but we can set that to be other percentages too. Okay? If something happens less than 5% of the time, we would call that a rare event, right, or a rare occurrence, a rare sample. That means that it might be statistically significant. That's what we'll talk about. In other types of research, like I said, you might want to change the significance level in order to check that something happens less often, right? So we'd expect that in behavioral research, something that happens less than 5% of the time might be rare, but we might not want side effects from a medication to happen less than 5% of the time. We might want them to happen less than 0.1% of the time. And so we'll use our hypothesis test that way, and we can get more detailed results. A hypothesis test is a way to investigate a particular claim about data that you have collected. Okay, the format of the test can be different. You'll see different types of tests in this class as we go along. You'll see other types of tests as you go along and read more things in the future. Okay, but the overall concept, everything you're doing is pretty much the same. You're going to collect a sample, and you're going to assume that that sample is no different from any other sample that you might collect. Then you're going to test to find out how likely it is that you chose that sample. Okay, if the probability of that sample happens less than 5% of the time, right, or if it's a rare event, then either you just randomly chose the rare sample, which is possible, okay, or maybe there's something different about that sample. And so if we're talking about average height, but if we randomly chose a sample of everybody who was basketball players and they were all 7 feet tall, and we compared the mean to the population mean, that's going to happen less than 5% of the time. That tells us either it's a rare sample or there's something different about the sample, right? And in this case, there's something different about the sample as they're all basketball players, they're all really tall. And so this is how a hypothesis test works. If it's really, really rare, right, or unlikely, then you're basically saying, well, since it's really unlikely to happen, then maybe there's something different about it. And since it's really unlikely for us to randomly collect a sample that contains all basketball players, if we have a sample of people who are all basketball players, well, maybe there's something different about those people, right? Maybe they're just all really tall. And so that sample in terms of height would be different from the average height. And there are two important statements when you have a hypothesis test. The first one is the null hypothesis. It is probably the most important. It is the statement of equality, or in later tests, the statement of no relationship. Basically, what you're saying is the sample mean that you've collected is equal to the population mean. Okay, we abbreviate this with an H0 or an H0, however you want to say it. Okay, in every hypothesis test, you should be able to write the hypothesis or the null and the alternative hypothesis in both symbols and words. The symbols will help you with the words, and if you have trouble with the symbols, then the words will help you with the symbols. We write the abbreviation for the null hypothesis with a colon, and then we're saying that the mean height is equal to 70 inches, or in this case, the mean height of the students in the sample is equal to 70 inches, depending on whatever we're talking about. It's always the statement of equality. We're always assuming that the sample we chose is no different from any other sample we would have chosen. Right? We always assume that the null is true. We start from there. Okay, the alternative hypothesis is what we think is happening. Okay, that's essentially making the sample different. Okay, the sample means different from the population mean, or it's greater than or less than the population mean. Okay, or there's some relationship between variables, which we'll talk about later. Okay, the alternative is sometimes written as H1, or you may sometimes see it as HA. In every hypothesis test, you should also be able to write the alternative in symbols and in words. In this case, the alternative with the colon, the mean height of the students in the sample is different from, the not equal to means different, from 70 inches. It can be greater than or less than, and we'll see some of that in just a second. The alternative is the researcher's best explanation for what's happening. You are not testing the alternative hypothesis. You're not going to prove the alternative hypothesis. You're not going to prove anything with statistics. You're just going to show whether things are likely or unlikely to happen. Remember that what you're saying when you say something is unlikely to happen and that it might be different, is that it could be the rare sample that you chose. You could have accidentally chose a sample of all basketball players. Okay, you can't know that for sure, but it's really unlikely that that happened. Okay, and so you always assume the null is true, and that's what you're testing. If the null is really unlikely, then your alternative is what's going to describe what you think is happening. There are two different ways that you can do these types of hypothesis tests, or hypothesis tests in general. Okay, a two-tailed test is when you want to determine if there's a significant difference between two groups, right, or between two values, or between, it depends on what you're testing, but you want to know if there's a significant difference. Okay, this just means you don't know if the values that you're comparing are going to be greater than or less than. Right? You don't know where it's going to be. It could wind up being a little greater than, could wind up being a little less than. Right? So you're not sure. And so what this does, it allows for probability on both sides of the normal distribution, or just the distribution. Okay, so if you have a sample that's much smaller than the average or much greater than the average, okay, they will be significant. They will be different. They will be unlikely to happen. Okay, so this allows us to choose a sample on either side of the mean. And so you get area in both tails of the distribution. Okay, this is, as you might recognize, the 95% value for z-scores. And that's what you see here in the pictures. If your research question is not really interested in just differences, but you want to determine if something is greater than or less than something else, then you would use what's called a one-tailed test. Okay, a one-tailed test can be left-tailed or right-tailed, depending on whether it's greater than or less than. Okay, you're only looking for samples that are much smaller in this case, or much larger in this case. Okay, in this case, the value of the test statistic, right, the critical value is a little bit lower, right, because now 5% of the area is on both sides. So let's look at writing some null and alternative hypotheses. Last year, the mean amount spent by customers at a certain restaurant was $35. The restaurant owner believes the mean may be higher this year. Okay, so if we wanted to test this, the null hypothesis would be that the mean is equal to $35. It's still equal to. The alternative is that the restaurant owner thinks it's going to be higher. He thinks it's going to be greater than $35. Okay, so we always assume that it's equal. Then we would test. We collect a sample of how much was spent at the restaurant, and then we'll compare it to 35. In a recent year, the mean weight of newborn boys in a certain country was 6.6 pounds. Doctor wants to know whether the mean weight of newborn girls differs from this. And so our null is that the mean weight, and we could just write a little g here, of newborn girls, is going to be equal to 6.6 pounds. We're going to assume that they're equal. We're going to assume that the samples we collect would be no different. And then the mean weight of the girls in this case, if he wants to know if they are different, the alternative would be that it is different from 6.6 pounds. Certain model of car can be ordered with either a large or a small engine. The mean number of miles per gallon for cars with a small engine is 25.5. An automotive engineer thinks that the mean for cars with larger engine will be less than this. And so our null is to assume that they're equal. We're going to assume that the mean for the larger cars is equal to 25.5. Was it miles per gallon? Okay. And then the automotive engineer thinks it's going to be less than that. And so we can collect a sample and we can test whether it's equal to 25.5 or less. In order to use these hypothesis tests, we have to determine if our result is significant, if it's unlikely to happen, right? We need to determine that probability. Is it less than 5%? There are lots of different ways to do this. You've even learned some of them already. Okay, we can use different methods to determine if the event is unlikely to happen. Okay, one way to do is confidence intervals, which we'll briefly talk about. Okay, but the other ways are what are called the p-value method. Okay, the p-value representing the probability, so basically just directly calculating the probability, or what's called the critical value method. Okay, and I'll show you both of these as we go along with examples in the next few sections. Recognize that all of these will be exactly the same. Doesn't matter which method you use to determine the significance, you should always get the same result. So the first method you can use are confidence intervals. Okay, you're familiar with calculating confidence intervals. Okay, we can determine if there are differences from our estimates from the population values or differences in the estimates from one another. The result from the confidence interval is interpreted depending on whatever type of question you're asking, right? So if you want to determine if the mean height of a sample is different from a population mean, you would calculate a confidence interval for your sample, okay? And if the population mean value is within the sample, if it's within the confidence interval, then they're not different. If the population mean is outside of the confidence interval, then they would be different. Okay? If you have two samples of IQ scores, you can find two confidence intervals. And if the two overlap, then there's no difference between them. If the two confidence intervals don't overlap, then the two samples are going to be significantly different. Okay? Confidence intervals are easy to understand how the test works because you can see where the two samples are separated from one another. They can be a little bit tougher to use in general. They're not the easiest way to do hypothesis tests. So we're not really going to do anything this way. You've learned how to do them to understand kind of how they work. Okay? And the confidence intervals can get you the same answers, but there are easier ways. One of those is the p-value method. To me, this might be the easiest way. Okay? The p-value just represents the probability that you would find the results given the null hypothesis is true. Okay? It is just the probability of choosing that sample. Right? And so once you find that probability, if it's less than your significance level, then it's unlikely to happen by chance. If the p-value is less than the significance level, then your outcome is rare or it's unlikely. And it doesn't matter how much less. It's not any more rare or less rare. Okay? It's just as soon as it's less than the significance level, we consider it a rare sample. If it's greater than the significance level, then it's not a rare sample. If the probability of choosing our sample is 50%, and that means that every other sample we collect will be just like the one we have. And so that means that sample is probably no different from the population. The p-value always represents that probability. The probability of finding your results given the null is true, right? Given that there's no difference between anything. Okay. The way we calculate it is slightly different sometimes, okay, but the way you interpret it, the way you understand that probability is always the same. It's always interpreted as the probability of your outcome, given that the null is true. Given that everything is equal, what's the likelihood that we found two samples that were different, right? If that probability is rare, then it would be significant. The last method is similar to what we were doing with confidence intervals in the past few sections, and it's the critical value method. We don't need to know exactly what that probability is to determine if there's significance. All we need to know is whether it crosses the boundary or not, whether it crosses that line of 5%. It doesn't matter where it is with respect to that line. Right? Once it crosses the line, it's a rare sample, okay, or a rare outcome. And so we can use critical values of the test statistic to determine if there's a difference. Critical z values, critical t values, things I've introduced you to over the past few weeks. If we're doing a two-tailed z test, which you'll see in the next section, you might recognize these z values as being the boundaries of the 95% confidence interval. Okay, but these would also be our critical values, okay, whether we do a one-tailed or a two-tailed test. Here's the two-tailed test, which would just mean if we calculated z and it was greater than this, and then the probability is less than 5%. You don't have to actually know what the probability is. Okay, this generally requires a table, like you see here, that you can get output from in Excel. But you guys know how to find the critical values for Z and T already from some of the previous videos, and you can do that way. If you're given the choice, I would always suggest the p-value method, but I'm going to show you the critical value method as well, and we'll do both in the examples that are coming up. If you have a rare sample, right, then we can reject the null hypothesis. If the sample is unlikely to happen, if the probability is less than 0.05 or less than our significance level, then we can reject the null hypothesis. Okay, we're going to write then the conclusion in the context of the problem to indicate that the alternative may be true. Okay, so there's evidence for whatever the alternative hypothesis is. If the probability is greater than 0.05 or greater than the significance level, if it's not a rare sample, then we don't reject the null. We've started out by assuming that the null was true. If there's no difference, right? If it's not a rare sample, right? If we could collect another sample just like it, right? Then we're not going to reject the null hypothesis. We're going to continue to assume everything is equal. Okay, there's not enough evidence to conclude alternative may be true. Okay, so the idea is first you make a decision about the null. That is always what your decision is based on. Do you reject the null or do you not reject the null? Okay, and we never write words like accept. Okay, it's either you reject or you don't reject. Sometimes you see fail to reject. Either one is fine. And then you write your conclusion about the alternative using what you've stated about the null hypothesis. As just a quick way to help you remember, okay, if the p-value is less than the significance level, then you have a rare sample. Okay, so you reject the null. Okay, if it's greater than or equal to, so it's exactly equal to 5%, that's still not rare. This is just a helpful thing to keep around until you get the hang of it, essentially. So let's talk about just some conclusions real quick. The veterinarian claims the mean weight of adult German Shepherds is 75 pounds. A test is made for our null, which states that the mean is equal to 75 pounds, and the alternative states that the mean is different from 75 pounds. Okay, the null hypothesis is not rejected, so we fail to reject. Okay, so there's, I'm not going to write this all out, but there's no evidence to support the mean weight is different from 75 pounds. There's no evidence to support the mean weight is different from 75 pounds. So you're writing about the alternative based on your decision about the null hypothesis. Let's look at another one of these. The mean caffeine content per cup of regular coffee at a certain coffee shop is supposed to be 100 milligrams. We do a hypothesis test. We're going to test to see if it's greater than 100 milligrams. The null is rejected. Okay, so we're going to reject the null. If we reject the null, what we're saying is that this sample is rare. It's unlikely to have happened by chance. And it's found evidence. There is evidence that the mean caffeine content, I'm scribbling this, you guys, so you don't have to just listen to me right, per cup is greater than 100 milligrams. There's evidence that the mean caffeine content per cup is greater than 100 milligrams. And so it's all based on your choice here, but then you write it in terms of the alternative. Because of the way that we choose a significance level, every time we run a statistical test, there's always a chance you can be wrong. That's why I tell you that you will not prove anything with a statistical test. There are two ways that you can be wrong. And what is a type 1 error is what's considered essentially a false positive, where you reject the null when the null is true. You say that something is different when actually they're not. So assume you get tested for the flu. The test tells you that you have the flu, but you don't really have the flu. Type 1 errors are controlled by your significance level. There's essentially a 5% chance that we're going to incorrectly reject the null. There's always that chance that it could have been a randomly chosen sample that was different. Right? There's always a chance you randomly choose a sample of basketball players. That chance might be really, really small, right, in general. Okay, but there's always that chance in the statistical test, right? When you set the significance level. That significance level is that 5%. It's allowing for there to be a 5% chance that we could have just randomly chose a really different sample. Okay, that's really unlikely to happen. Okay, but it can happen. That's allowing for it. That's the false positive, right? That you find a sample that's just randomly different when it was just randomly different. It didn't have anything to do with the height of the people in the sample. A type 2 error is what's considered a false negative, right? This is when you fail to reject the null and the null is not true. Okay, this is failing to find a difference when there actually is a difference. right? The flu test tells you that you're not sick, but you really are. Right? It tells you that you don't have the flu, but you really do. Failing to reject the null when the null is not true just means that you're not able to essentially dig deep enough to find the differences between the two values, right? But you wouldn't know that from the test. So maybe you really, maybe if we want to talk about heights of, maybe you really do choose that sample of basketball players, but your test isn't specific enough to find the difference in height between the two groups. That would be a type 2 error. Okay, type 2 errors are not controlled by the researcher. They're not directly, they're controlled by the way you design the experiment. They're controlled by eliminating all other explanations. So as we go on to this last section, I wanted to share with you just the steps that we're going to take for each hypothesis test. And you'll see this in each of the examples in the next section as we go along. But if you follow these steps from beginning to end and use what you learned in this section and what you've learned already in the class, then every hypothesis test is just all the same 4 steps. What you do at each step is slightly different, particularly steps 2 and 3 sometimes. Overall, you'll see that you can use these steps for every hypothesis test that you do. I'll show you that in the next section. Please let me know if you have any questions.